Hello, everyone. Welcome to today's webinar called Parallel Programming in Wolfram Language. My name is Dimitar. I work as a technical content writer at Wolfram Research Europe, where I do a lot of these webinars that we do every week, and we have all sorts of different topics. But this week is parallel programming. Um, Today we'll be talking about what parallel programming is, how to use it, when to use it, and kind of how to customize it so it can do what you want it to do. I think we're scheduled for an hour and a half. The webinar might be a bit shorter, but that's a great opportunity for you to ask your questions because we can have time for a nice discussion. And in my opinion, this is a really interesting topic. So if you do have any questions, feel free to put them in the chat if you're watching, in the Q&A tab if you're watching on Big Marker, and in the YouTube live chat if you're watching on YouTube. Having said that, let's get into the kind of the plan for today's session, what we are going to cover. We'll start obviously with an introduction, the basics meaning the basic functionality of how to use parallel programming in Wolfram Language. Then we'll go into some more specifics, automatic parallelization, parallel analogs, and then we'll go into kind of more customization, fine tuning, like manual control, sharing state tuning. Remote computation, we're probably not going to talk too much about that, just because it's not that related to parallel programming. But we'll mention things like remote kernels, cloud computations, and so on. But the basic idea is anywhere you can do computation with Wolfram language, you're also able to parallelize it. So whether that's on your local machine, whether it's on a different machine on your local network, whether it's on the Wolfram cloud, or whether it's on something like AWS or any of the similar services, anywhere where the Wolfram kernel can run and do computations, it is also able to do parallel computations. So that's the basic idea. We'll finish off with a little summary at the end. So let's get into it. So let's start with just with a brief overview of what parallel computation is to begin with. Now, I'm sure all of you know that modern day CPUs, I think almost universally now, they're multi-core. So I think even budget laptops come with at least dual core, maybe even 4 cores on their CPUs. So typically the advantage of having a multi-core system is that if you have different applications running, one of them can run on one core while another runs on another, and so on. So that kind of splits off the load between different logical processors, and that ultimately speeds up your user experience when you're using your computer. So for example, at the moment I always have Mathematica open. I have Google Chrome, where I'm keeping an eye on your questions in the chat. So Mathematica would be running on one core on my system. Google Chrome would be running on another. And that's why, for example, if something like Google Chrome freezes, which it does sometimes, that means that the rest of your computer can run normally and things like that. That's kind of a simplified view. The way your operating system delegates things to different cores is a bit more complicated than that, but that's kind of the basic idea. We have different cores and we're using them to perform computations in parallel, hence the word parallel computation. So as I mentioned, I'm running Mathematica, so any code by default, if I don't specify any options, any code that I run in Mathematica, and that goes for any programming language, by the way, any code that you run runs on a single core. So if I have some loop, let's say for loop, or in the case of Mathematica, table or do, where some operation is performed on a list that has, let's say, 100 elements. When I run that code, these 100 computations are done sequentially. So meaning that the first one is done, and then the next one is done, and then the next one is done, and so on. So the value and the promise of parallel computation is that we can, if we have 100 computations, we can delegate them to different cores, and we can do more computations at the same time. We can do more computations in parallel. So that's kind of the idea. And this graphic that you see here on your screen is just kind of a simplified, again, very simplified diagram um, of how parallel computation works. So you have a task manager which delegates computations to different workers, and for for the purposes of this webinar, you can think of workers like CPU cores. So in this case, let's say we have a 4-core CPU, quad-core CPU, and we have some computation, and the task manager delegates each piece of computation to a different core. Um, that core does the computation. It returns the result to the task manager, and once the task manager has collected all the results, we get back our output. So that's the idea behind it. I mean, you can already kind of recognize that it's a very powerful idea and very powerful promise, because this is just an example with 4 cores, but as you see, so the computer that I'm presenting from and that we're all presenting from here in Wolfram Search Europe has 24 cores. So that means that we have 24 workers that can do tasks in parallel, instead of having these, let's say, again, to take a simple example, a computation with 24 steps can be done essentially in the time it takes for one step to be done. There are some caveats to this, but that is the main idea. We'll get into the caveats, because the way I described it just now sounds like we should always do parallel computation, because why wouldn't we want things to run on multiple cores at the same time? And the short answer is that all this process that you see on your screen, where the task manager delegates computations to the cores and they return it and the task manager collects it, all of that incurs overhead. And sometimes that overhead, the cost of that overhead is higher than the value you get from parallel computation. But that's the basic idea of parallel computation. So if you're not sure how many cores your CPU has, there are different ways to check it, but you can do it from within mathematically using this dollar variable, dollar environmental variable called processor count. And when I run it on this computer, I can see that I have 24 core CPU. So that's going to determine how many workers I can spawn to do calculations for me in parallel. Okay, so as I said, the promise of parallel computation is great, but um, it's not always going to be the case that you're going to save a lot of time by doing parallel computation. So when should you do it, and how much is it going to help? Parallelization is especially good for long and heavy computations, as you can imagine. And in fact, if you are just maybe if you're just playing around with some of the parallel functions and you give it simple computations like iterate over the list of the first 1,000 primes, for example, it's a very simple computation for modern CPUs. So if you try to do that in with parallel computation, you probably see you're probably not going to see any benefit from that. But if you're doing something that is especially intensive and computation heavy, that's where you start to see the benefits of parallel computation. So if you have a piece of computation, like say training a machine learning model, and it takes 4 hours to do it, if you have 4 cores, if you could split that into different parts, um, that's when you'll kind of see the benefit of parallel computation, or that's one of the cases where you'll see the benefit of parallel computation. Another very important condition is that the tasks that you do can be split into subtasks. So sometimes you have a piece of computation where there are, let's say, 20 steps, but each step depends on the result of the previous one. So in those cases, you are just not able to. I mean, you can run the parallel functions, but the course will still wait for the result of the previous computation. So you're not going to see any benefit. You just incur the penalties of the overhead that's involved with parallel computations. But in many cases, you have computations that don't depend on previous steps. So I think a simple example that I was just thinking about is I did a webinar on extracting data from web pages, and I had an example where I get the text from news articles from the BBC or from any news website. So I think that's a kind of simple and illustrative example where if I want to get, let's say, 50 articles from the BBC, so that's obviously 50 steps in a sequential computation terms, but these steps don't depend on each other. So getting the first article is not a prerequisite for getting the second article. They can be done completely independently of each other. So that's an example of a case where parallel computation is especially useful, or just useful at all. Um, Tasks with small inputs or outputs, and the main idea behind that is it minimizes the overhead, because if we go back to the graphic, if the task manager is passing large chunks of data to the workers and then the workers are passing it back, that increases the overhead, and you might still see benefits of parallel computation, but it's more likely that you don't. So I think, just in general, when do you use parallel computation? I think it's highly situational. So the main thing I want you to take away from this webinar is that it is not that you should use parallel computation all the time for every single thing. Um, what I would really like to impress on you is that it is a tool that's available to you. And if you find yourself in a situation, especially if these conditions are met, I want you to have it kind of in the back of your head that this is something that could speed up your workflow. So, how much can it speed up your workflow? That's our next section. So, as I mentioned, there is some overhead. So, if the overhead is a price worth paying for your computation to be sped up, that's going to help a lot. If it's not, um, then it's not going to help that much. Any data required for a task will be sent to workers sequentially. Um, so instead of passing the data itself, we pass references or pointers. And you don't need to worry too much about that. As far as the end user is concerned, your workflow is either going to be sped up or it's not going to be sped up. So and there's a quote here on those low. The overall performance improvement gained by optimizing a single part of a system is limited by the fraction of time that the improved part is actually used. So this is more kind of from an architecture point of view. Don't spend 20 hours optimizing some part of your code to use parallel computation if you're going to run that piece of code 2 times in your life. So it's just not worth the time investment. But it's worth keeping in mind, because sometimes we get too excited about doing things nicely and neatly, um, that we kind of get lost in the details, and we actually spend more time than we are saving. Which, if you're having fun doing it, I don't think there's anything wrong with that. But if you're, it really depends what you're optimizing for. If you are in a position where you need to optimize for speed, then it's probably not. In some cases, it might not be worth it. Um, but yeah, that's a brief overview. So let's get into some basic functionality. All right. So to use parallel computation, we need to have kernels, and we always have a kernel when we use Mathematica, but we just have one. As I mentioned before, it runs on a single CPU, and for all intents and purposes, you can use kernels and CPU cores interchangeably. They are not the same thing, but as far as parallel computation goes, one kernel can run on one CPU core, so you can use them interchangeably. And the way you launch more than one kernel is you can use this launch kernels command. And if you don't pass anything to it, it's going to launch as many kernels as your computer can support. So in my cases, hopefully these should be 24. And you can see you have a really nice status bar where you can kind of monitor as the different kernels are getting launched. And it should be a bit faster, but that's okay. Um, and what launch kernels outputs is kernel objects, where you have some basic information about each of the kernels. The most important one that you care about is the kernel ID. and we'll see we're going to use that piece of information in some of our code later on. Um, but you have a few other pieces of information. Um, there is a way in which the maximum number of kernels you can launch interfaces with the type of license that you have. I am not too familiar about that, um, but it's worth keeping in mind. So if you're seeing less kernels than you think you should be, that might be the reason. Um, just before I go on, just looking at a few questions on Big Marker. Amin is asking, are these concepts applicable to Mac M series as well? Absolutely, they are. Yeah. Mac M series are really nice CPUs. And they have my personal laptop is an M1 MacBook Air, which has 8 CPU cores, and I can use parallel computation with 8 kernels. So they are absolutely applicable. What you're going to see, probably the only thing that's going to be different is, I think there was a yeah, there's an environmental variable called processor type, um, which gives you the kind of the architecture of your processor. On most Windows machines, you're going to see x86. If you run this environmental variable on Mac, it's going to be ARM. But for everything that I'm going to be talking about in this webinar is going to work on your Mac. And Christoph is asking if I could increase the font size a little bit. Yes, I apologize for that. Should have done it. Hopefully, this is a bit better. You can access the notebook as well. There is a link in the chat, both on YouTube and Big Marker. So if you wanna look at it while we're going through it, that's also an option. But let's get back to our code. So we've launched as many kernels as we can launch. So let's see what we can do with them. If we try to run it again while we have the kernels, we're just going to get an error that says that we already have kernels running, so we're not launching anymore. We can check how many kernels and which kernels we have running just by using the kernels command. And that just gives us a list of all the kernels. If there is an ongoing computation that's being done by the kernels, you can abort that using abort kernels. And again, if you don't pass it any arguments, it's just going to abort the operations on all kernels. So in this case, I wasn't doing any operations on them, so it just gave me back a list of the kernels. And if we want to close them, so if we want to shut them down completely, we can just use close kernels. So that's the and you see that once we close them, the state is defunct, meaning that we're not able to use them anymore. And if we want to do parallel computation, we need to launch them again using launch kernels. So those are kind of the main functions related to managing the kernels, managing the kernels in your session. There are some global variables. I mentioned some of them already, but the kernel count gives you the number of currently running kernels. Or currently running subkernels, I should say, because obviously my notebook is running on a kernel, but this gives me 0, so I imagine it's referring to subkernels. Processor count, as I mentioned, the kind of the logical processors on your computer, and then we also have some. Why is this kernel? Yeah, we have a few other variables related to kernels, and also related to your CPU. We actually saw both of those, but yeah, just some global environmental variables related to your machine and your session. There's also a graphical user interface option um, for configuring and getting information about your kernels, and that's in the menu. I can show you instead of showing you a screenshot, I can show you on the menu here. If you go to edit preferences, there is a special subsection for kernels, and this is where you can see things like how many kernels are running, what the behavior should be of Mathematica. By default, kernels are launched when they are needed. So I showed you how to launch them manually. But normally, if you run some function that depends on parallel computation, um, they're going to be launched automatically. I say normally because it doesn't always happen in my experience, but it works like 90% of the time probably. But this is where you can kind of define that behavior. You can have it as completely manual. So every time you want to do parallel computation, you need to launch the kernels manually. When needed, tries to launch them when they're needed. But as I said, it's not foolproof. So that's something to keep in mind if you're trying some parallel function and it's not working. It might be because you need to launch the kernels manually. Or you could have them launch at startup. So if you know that you're always going to be using multiple subkernels, um, you can have that option as well. And there are a few other things you can kind of specify here, but it's pretty much basic stuff. Just a menu to see some configuration options. And obviously on macOS, it looks very similar um, to that. It's in the same place. It's in the preferences and in the parallel submenu. Okay, so far we've been looking at kind of managing kernels, but let's actually start doing things with them. So we'll start with kind of fairly high level all-purpose function called parallelize. And what parallelize does is it takes any piece of Wolfram language code and it tries to um, execute it in parallel. So um, well, let's see what the examples here are. Let's launch. So in this case, we're launching 4 kernels. We see their IDs, and what we're doing is we have this normal piece of Wolfram language code, which is just a table, which is just a standard iterator function in Wolfram language. Which, um, if we just run this piece of code, we're going to get our normal output. And what we can do is we can just wrap this whole thing in this parallelize function, and it's going to make sure that it is using as many subkernels we have available to kind of delegate pieces of this of whatever is inside it. So here, when we pass it to parallelize, it uses these 4 subkernels that we just launched, and obviously the result is the same. So this is an example of function where um, each step is independent of each other step. So that's a good example of a parallelizable function. Um, as I mentioned, parallelize is kind of all-purpose. It just takes anything you pass into it, and if you pass it something that's not parallelizable, then it's just going to throw a warning saying, "I'm not able to do that. We'll just proceed sequentially," and it's just running. It will just run the function sequentially, so it will be the same as if you didn't use parallelize at all. Um, But other than the all-purpose parallelize, we have kind of parallel analogs to different built-in functions. So table is something that we use quite often in Wolfram language. So that has its kind of parallel equivalent, which is just called parallel table. And what parallel table does is exactly the same thing as table. It just delegates that to as many subkernels as it can. So here, instead of using parallelize and then giving it a table, we can use parallel table. Functionally, it's the same thing. Here's an example of when you try to do something that is not parallelizable. You get this warning here saying that this cannot be parallelized, proceeding with sequential evaluation, and you still get your normal result um, as you would expect. So it's not something that um, that would give an error or crash your program. It's just it gives you a warning. Let's get into a few more um, parallel functions. So parallel evaluate is a function that will run a copy of the same computation on each subkernel. This can be useful for checking or averaging results. Um, do we have an example for this? We do. So here we are going to start using um, the ID property of each subkernel. So here we're passing the same function, which is kernel ID, but we're passing it with parallel evaluate. So what parallel evaluate does is it gives this function to each subkernel. We're basically asking them to identify themselves, if you want to think about it that way. Um, but when this kernel ID function is run by kernel 25, obviously it gives 25. When it's run by kernel 26, it gives back 26, and so on. Let's see, what else do we have? Generate a random number for each subkernel. So okay, that's a good example of parallel evaluate, because every time you run random real, obviously you get a random real number. Um, so we're using parallel evaluate to pass this random real function to each one of our subkernels, and obviously they all return different results because each one gets a random number. So the other code here is just to frame them and to make it look a bit nicer. We can also choose a specific subkernel to run our computation by passing the kernel ID, and here we're just using this subsetting function, which gets the first subkernel that we have running. So this is going to be all of them, and here we're just subsetting the first one. Um, Normally, if you have any variables, any symbols, any functions, they're going to be distributed among subkernels automatically, so you don't need to worry about. We'll see a bit later on in the webinar when we have functions in custom contexts, in a custom scope. Then we need to do some extra work to make them available to all the subkernels. But anything you define on the top level in your notebook, you don't need the subkernels already know about it, so you don't need to worry about that. And here we just have a simple function, and we can say that we can see that when we pass it to parallel evaluate, it runs it without any problem. Okay. Um, Parallel analogs. We kind of mentioned parallel table previously, but here's a few more examples using parallel table. And here's a diagram. If you're kind of a visual learner, that probably helps you a bit more than kind of explanations in English. But when you have a parallel function which applies f to I, and I goes from 1 to k, um, uh, here's how the process looks like. It starts with f to 1, f to 2, so on to f to k, sends it back to the task manager, and you get back the result. So this is just a visual explanation of what I have been talking about. So let's look at some examples. Here we're using table uh, to run a table, well, to run iteration over I, where I goes from I to twice the kernel count. So we have 4 kernels running, and so we're doing 8 computations. So essentially, I think the next example will probably show it, but each subkernel is running 2 computations. So you see here on the parallel table, each output is marked with the ID of the subkernel that produced that output. So you can see that the first two were produced by kernel with ID 25. The other two are 26, and so on and so on. So here's something I mentioned at the beginning, that for short computations, the overhead involved in parallel table makes it actually slower than table, even though we're using multiple cores and all the operations are done in parallel. It's still slower because of the overhead that I mentioned, related to setting up the whole kind of infrastructure for parallelization, and passing data around. It actually makes it slower. So let's see if that is actually true, and you can see that it is. Um, we're just running a simple table that squares I, where I goes to 10 to the power of fourth. Just a very basic arithmetic computation. And you can see that when we run it with the normal table, we get a very quick, we also have this suffix here, repeated timing, which measures how long it takes for this computation to be done. And you can see that when we run the normal table, we get a really low number. And when we run the same computation with parallel table, it's still very quick, obviously, but it takes substantially longer than the normal. um, table. So this is an example where, again, this is a very simple um, arithmetic computation that takes less than a fraction of a second to run. So in cases like this, you're not going to see any benefits of using parallel table. However, if you give it something a bit more complicated, the overhead becomes less important. So again, here we're doing the same thing using table and then parallel table, and we can compare. So this time you can see that parallel table is almost 3 times quicker than table. And why is that? Why the change? Well, just simply because the actual computation takes longer. So you can see that the normal table computation takes more than a second, which in CPU time is quite long. So in cases like this, if you have long computations, breaking them down and passing them to subkernels is actually going to benefit you. And here's a very useful or kind of informative graphic. I believe it's this one where it kind of shows you how. All right, so let's look at it. It compares table and parallel table, a- and here you kind of see the time it takes. So for very simple computations, you can see the table is actually quicker, but as computations get more complicated, parallel table becomes quicker. Um, Parallel do. So here we're going to run through a few other kind of parallel analogs of just normal Wolfram language function. So just like we had table and we introduced parallel table, we're going to do that with a few other kind of very common functions. The first one we have here is parallel do. And do is just a very basic Wolfram language function iterator, very similar to table, but it doesn't actually output anything. It just iterates over a list um, without outputting anything. And here's a comparison between parallel table and parallel do. Both of them do the same operations, but you can see that parallel table, and that goes for the normal sequential equivalent. If you just use table, it gives you back the resulting list. If you just use do, it doesn't give anything back. It just does. So here we have a few examples with a pause. The reason why we're getting an output here is that um, we actually have an explicit print statement. So that's why do actually returns something. It's actually print that returns something. It's not do. Um, but what we're doing here is we're pausing for 1 second and then we're printing I, where I goes from 1 to 4. So you can see it's a good illustration of how parallel do differs from the sequential do, because if we do parallel do, um, each of these 4 computations, you can think of these as 4 computations. Each one of them with parallel do is going to be passed to different subkernels, so they'll return all at once or all after 1 second. Um, and obviously, if you're doing them sequentially, it takes 4 seconds because you're pausing between each one. If you're doing them in parallel, it takes 1 second with 0.11 overhead. Um, Parallel task may be evaluated out of sequence. So while the task manager passes each computation to each subkernel, they all work in parallel, which is kind of the purpose of the whole thing. But some of them might return their results um, quicker than than other ones. So you're not going to get the resulting list in a perfect order. Whereas if we do just normal do, you'll get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's something to keep in mind if you're doing any computations where the order of the elements in your output matters. It's something to keep in mind. More parallel analogs. We have some for some basic arithmetic. So we have parallel sum, parallel product. Oh, actually, it's only these two. So let's run through them. Sum again, very obvious what sum does. Parallel sum does the same thing, just in parallel. And here, if you have some more kind of intensive computations, you'll see that parallel sum is probably quicker. So let's run this, which gets the Euler phi of I, where I goes to 10 to the power of 6. And you can see that parallel sum on that computation is almost twice as fast. Well, not really, but it's faster than the sequential sum. Anna is asking, is there any way to know in advance how much time a specific computation with or without parallelize will take? That's a very good question. And I wish there was a way to know that, because that would make it much more easier to choose when to use parallelize, when to use parallel computation in general, and when to use sequential one. But unfortunately, the only way you can know is to kind of test it yourself. Um, in that case, this repeated timing suffix is very helpful. So if you're wondering whether it's worth parallelizing a part of your code, um, run it with the parallel function, run it with the normal one, and then compare the timings. If the parallel one is substantially faster, then it's worth it. If it's not, then it's not. But there's no better way to know that in advance. The only way to know it is with experimentation. There are some rule of thumb that you can kind of follow. So if something takes less than a second to run, then it's probably not worth parallelizing. But other than that, it's just trial and error. Um, Moving on, parallel product, same idea. Gets the product of something, and if that something is a very simple computation, you're not going to benefit from parallel product. Actually, let's have a look. I think in this case, the parallel function will be slower for the simple computation than it is. Oh yeah, definitely. You can see that parallel product takes a lot longer to execute. But when we use this kind of a bit more intensive computation, that's when you start to see the benefits. Parallel map. Map is one of the most common functions, at least that I use in the Wolfram language. You might know it by its shorthand, which is this. So when you have some function and you want to apply it to a list of numbers, it looks like this. So if you're doing something, oh, actually f is defined. I was wondering why I got real output. But basically, if you are applying a function to each element of a list, you're probably doing it with the shorthand. Or if you're reading somebody's code and you see this, that this stands for map. Um, so what parallel map does is it does the same thing, just does it um, in parallel. So here we're mapping f, which is already defined, as we saw. We're mapping that function um, to each kernel. Because we are doing it sequentially, we're just doing it on a single kernel, which is our main kernel, which has an ID of 0. And when we do it in parallel, each of these computations is passed to a different kernel, and then you see their IDs here. You can see that these results are collected from the operations of different kernels, and these are their IDs. Parallel array, similar idea. The normal array function, nothing interesting there. Parallel combine is a slightly interesting one because there is no sequential equivalent of, there's no combine function as far as I know, or maybe there would be. I don't think there is. So what parallel combine does, and it's a bit it's a bit difficult to explain, and it's even more difficult to come up with a good example that shows the utility of parallel combine. But let me try to explain to you what it does. So it essentially takes three arguments. It takes f, the function, it takes a list that is going to apply the function to each element of that list, and it takes a third function, g. So when you execute parallel combine, f gets applied to each element of the list, just as if you are doing map or parallel map. But then once that Once that process is finished, it applies this G function to the output of the first two, if that makes sense. I think in this case, probably the graphical representation is the clearest one. And you can see that G gets applied to the result of F being applied to each element of the list. Um, it's a bit difficult to explain, and to be honest, the examples don't make a lot more sense. But it's just a different visualization of what parallel combine does. So here we're applying P to the range of 2 times the kernel count, and once that has been done, we're applying Q to the whole result of this computation, and you can see the result here. Um, Again, this example here, we're constructing essentially our own parallel version of map thread using parallel combine, which is not necessarily a good idea because the um, the built-in function is significantly faster, especially when you're threading over a small number of lists. So you can see that um, the map thread, that this is a built-in function in the Wolfram language. Um, it's much faster than the one we just created. But if you do something more complicated, again, it might be worth it. And again, parallel combine should only be used for operations where the output does not depend on the batching of the inputs. Okay, so let's get into a bit more manual control of how our parallel computations are done. Parallel try um, works kind of like parallel map, but as soon as one of the kernels has finished its computation, then it aborts all the other ones. So you pass, in the most simple example, let's say you pass 4 elements to 4 subkernels. One of them is going to finish before the others, and as soon as one of them finishes, then that result is returned, and all the other ones are discarded. So you can see this. Um, Here we are doing we are pausing for a certain number of seconds, and then we're returning the number of seconds. So you can see when we do that's actually quite a neat example, because when we do this in parallel, each of these elements in the list are passed to different subkernels. So while 4 is the first number to be passed, obviously it's going to take the longest time to execute because it's pausing for 4 seconds. Even though 1 is the last element to be passed, the subkernel that receives 1 only has to pause for 1 second and then returns the result. And as we said with parallel try, as soon as the first result is received, everything else is discarded. Um, and we can pass, instead of only waiting for the first result, we can wait for the first n results, for where n is any number up to the number of subkernels that we have. So here we are doing we're looking for the next prime after a specific number, and we're saying that we only want the first 3 subkernels that get the result, and the last one, because we have 4 running at the moment, the last one we don't care about. We just want the first 3. So again, a bit difficult to come up with a good example where this would be supremely useful. But again, it's one of those things that it's useful to keep in your mind, because in many cases when you kind of learn something, you struggle to think of, oh, when am I going to use that? But then later on, maybe a few days later, weeks later, months later, you come across a problem where it reminds you of something that you've read in the past. So I think, but if you have any good examples off the top of your head, I'd be interested to hear about them. But I don't with parallel try, to be honest. Um, Parallel submit, wait next, wait all. So parallel submit submits a task but doesn't actually execute it. So it kind of prepares a computation on a subkernel, and then you need to use wait next or wait all to actually execute that computation. So let's see what it looks like. Here we have parallel submit with a table where we have four numbers, four computations essentially. I goes from 181 to 184, and we have 2 to the power of I minus 1. The actual computation doesn't matter. What matters is that we're using parallel submit, which instead of computing the result, doing the computation and giving us back the result, it prepares the computation, and you see this nice object here which says ready for processing. So basically what that is waiting for is waiting for you to tell it to actually compute the result. And the way you tell it to do that is using wait next and wait all. Um, wait next just does the first computation in the queue. So you can see in this case we have four. Um, when we um, when we use wait next, it does the first one. Um, and what wait all is going to do is to execute all of the tasks that are waiting to be executed. Um, Here, a bit more dynamic example where you can actually, well, you can't really see it because it happens so quickly, but it gives you kind of a lot of these objects, status objects, and things like that in Mathematica are very kind of they're a very succinct way of representing some underlying information. So here we're just watching the scheduling and the actual running of the tasks as they're happening. Is there anything else to mention here? The actual computations again don't really matter. It's just we only care about the parallel aspect of them. So I'm not going to go into much detail into what's happening here. Okay, so so far we've just been using um, we've just been using variables and functions that are in our global context. So anything you define in your notebook is understood to be in the global context, so you can use it anywhere in your notebook, and that also applies to subkernels. Subkernels are automatically aware of things that are in the global context, but sometimes you have things in custom contexts, and in those cases you need to explicitly share the definitions of the objects in a custom context with the subkernels so that they know about them. Here we probably have some examples. So this is an example of just how you would normally write a function in Wolfram language, and you can get the context of that function using this context function, which gives you back the context, which in this case is global. So we can, if we have a function in the global context, we can automatically pass it to parallel evaluate. It knows the definition of that function, so it's just going to execute it, no problem. But here we're defining a function that has a custom context called myContext, and this backtick stands for context. And then after that we have our actual function. So if we try to do this, if we try to pass a function that's defined in a custom context to a parallel function, it's not going to work. And as you can see, here we're asking for the kernel ID, and we're getting zeros because it's all run on the main kernel, because the main kernel is the only one that knows the definition of this function, because it's defined in a custom context. So the way we can make our subkernels aware of this definition is by using distribute definitions, and then we have the context and the actual object that we want our subkernels to be aware of. And then after we do that, we can just use it in parallel evaluate, and you can see that in this case we are getting the computations are done by the actual subkernel. So um, the computation is actually run in parallel now. Um, and um, you can clear the way you clear a distributed definition. So if you have made a definition available to your subkernels and you want to make it not available, um, first you clear it and then you distribute the clear definition to the kernels. And then after that, you get back to your to the state where the subkernels are not aware of it. Um, so this distributed definitions is used for functions. We have the same thing with shared variables. So same ideas, but just for variables. So if you have a variable in the global context, you can um, if you have a variable in the global context and you pass it to your subkernels, um, each subkernel gets its own copy. So that's why when you evaluate it in parallel, you get 111 because each one of these is executed on a different subkernel independently of each other. Um, so if you want to have a variable where all of the subkernels are seeing the same variable, you use this set shared variable function. And then when you iterate over it, each subkernel is aware of the state of that variable in all of the other subkernels. Um, you can use this environmental variable, shared variables, to see which variables um, have been shared to all the subkernels, and the way to unset them is using unset shared. Again, very similar idea to the functions, just for variables instead of functions. Um, Set shared function, again, very similar idea. I'm going to go through all the details because it's very repetitive. But the syntax, as you see, is kind of consistent between each one of them. You have shared, set shared variable or function. Um, you have unset to unset it, and so on. Um, Robert is asking, can parallel submit be used sequentially? I'm trying to improve a recursive calculation, chromatic polynomial, and I think I'll need to submit new tasks almost continuously. Um, Can parallel submit be used? Yes, yeah, parallel submit can be used sequentially. Yeah. Um, so, well, there are different ways you can accomplish that, but let me go back to the parallel submit just so I can give you some pointers. So this is the parallel submit. So what I would do, I'm not familiar with the specific calculation that you're trying to do, Robert, but the way I would approach it is I would queue all of the calculations that you need to do um, using table or any iterator, um, and then y- the way if you need them to run sequentially, you can use wait next, again in a loop or something like that, where you can ensure that they are not run at the same time, if that makes sense. But yeah, you can definitely use them um, sequentially. So going back to critical section, this is a bit more interesting. Um, and again, the best way to describe this one is through a graphic. So in this case, the actual picture of that on Wikipedia is very useful. So let me share that with you. Let me put it up on the screen. So here we have two two computations, two processes that are running in parallel, and they're both doing their own thing, but there is one element that they are both relying on, and you can call that critical section. So you can see the problem is that if the first process modifies this variable before the other one does, um, the other one will see a different value. So in some cases, that's not what we want. We want both processes to do their parallel computations independently, but when they get to a certain variable, we want them to stop and process it sequentially. So in that case, we can, and hopefully that's clear. Again, a bit difficult to explain, but hopefully the graphic makes it a bit clearer. Um, and if we want to accomplish that with code, we can use um, we can use this code here. So we're setting um, where is the critical? Yeah, critical section. We're using critical section, and we're defining a lock variable, and then we have our parallel computation code, which is going to ensure that um, that lock variable is locked and is operated on sequentially. Um, Parallel needs. So this is when you're importing um, different things like different packages, packlets, things like that. Typically, the syntax for doing that is you use needs and you import your thing. So the one I typically use is rlink, I think. So um, by default, when you import that, only your main kernel is aware of these definitions. So again, just like we were discussing about the custom context of functions and variables, you need if you want to use a function that comes from rlink or computer arithmetic or any of the other packages that you can import, you need to make them available to your subkernels explicitly. And the way you do that is with parallel needs. Um, so here we're using something from the parallel needs package. And first we make it available with parallel needs. And then after that, we can pass it to any parallel function. Um, and then it knows it has access to all the functions in that package. All right. So finally, we'll get into some fine tuning of your parallel computations. And that comes in addition to whether parallel computations is worthwhile for your problems. So this is just further refinement to make it even quicker, even more optimized if you need it to be. I would say in most cases, you probably don't need to go into um, that fine grained detail, but it is there, and it can make a difference in some cases. So it's useful to know it. Um, the first thing we can specify is the grain size of the parallel computations. So there are two extremes. So you can either have a small grain or a large grain, and that if you specify a small grain parallel computation, it tries to break up the computation uh, into as many different computations as possible, and it passes those to the kernels. Um, so in the case of small grain, means more efficient use of the CPU at the cost of the of more communication between workers. So because we're breaking up the computation into as many steps as possible, our task manager needs to communicate to the subkernels more frequently, which increases overhead, um, but it is using the CPU more efficiently. Um, and the way you specify that is anytime you have a normal parallel computation, you can pass this option called method, and method takes either finest grain or I think this is coarsest grain. Yes. So let's see an example here, and well, actually more important is when you would actually use it. So this is suitable for computations involving few calculations where evaluations take different amounts of time. As I mentioned, it leads to higher overhead, but it maximizes load balancing. So with a lot of the with the fine tuning, you're kind of balancing between overhead and efficiency of the calculations, efficiency of the CPU. So you can see it can, in some kind of very specific edge cases, it can make quite a big difference. Um, Here, I mean, the difference is not radical, but there is a difference. Um, and so small grain or finest grain is kind of one end, one extreme, one end of the spectrum, where large grain is at the other end. So, but again, the idea is the same. You specify. Um, so what large grain does is it breaks down the computation into as few steps as possible, and it passes those to the CPU. Um, and we can see that uh, again, you can see that the difference here is also, I mean, in absolute terms, it's not massive, but there is a difference. This method is suitable for computations involving many calculations, all of which take the same amount of time. It minimizes overhead, does not provide any load balancing. So if you have a lot of computations where you know that they take exactly the same amount of time, courses grained is going to give you some benefits over leaving the default. And by the way, if you don't specify any method, there are some heuristics that will try to determine which method is used, but normally it will be some reasonable middle ground. Um, I will try to optimize. It's not going to be one of the extremes. Um, so if you don't want to go into this kind of fine tuning, um, leaving this option out entirely is going to give you a reasonable kind of compromise. Um, but as I mentioned, large grain and small grain are kind of two extremes on a spectrum. You can actually pass a custom grain size where you explicitly specify how many evaluations should be done by each kernel. And here you can see that we pass it. We use a different option. Instead of coarser grain, finest grain, we use evaluations per kernel, and we can specify a specific number. Um, and then that number could be anything. Well, it could be any number that you want. No more than that number of computations to be done by each kernel. And item, there's another option called items per evaluation, and that method will break the computation into evaluations of at most m calculations each. So here we specify 3. Um, and you can see that the first kernel is running the first 3 numbers, the second one is running the second 3, and so on. Again, as with the decision of whether to use parallel computation or not, um, deciding whether to use fine tuning or not is mostly a matter of trial and error. So if you're already using parallel computation, I would say first start with experimenting with the extremes. See if coarsest grain gives you a better result than finest grained. Um, if it does, just use that. Again, there are some kind of heuristics you can use, such as if you know that each computation takes the same amount of time, finest grain is probably going to yield better results, but a lot of it is still down to kind of trial and error. So you can think of all these kind of fine tuning options as different levers you can pull that you can experiment with. So you don't need to worry too much um, about what they mean. Um, you can just experiment with them, and if they result in faster calculations, just use those and not the other ones. And again, if you don't want to go into all of that, to just leave them as the default. Oh, there is actually an explanation here. Default is automatic, and it's usually a compromise between overhead and load balancing, which with all of these fine tuning methods is what you are balancing between. Um, so finally, we have um, a summary of what we have been talking about today. So there are a few things to consider when doing parallel computing. The size of the task, as we mentioned, if it is a computation that takes less than a second, it's probably not worth it. Um, it's not worth trying to parallelize that. Another thing is how often do you use it? Because even if something is, let's say something takes 10 seconds, but with its parallel equivalent takes 5 seconds, that sounds like a big win, right? But if you only use that function once, and you say 5 seconds in total, it's probably going to take you 5 seconds, more than 5 seconds, to actually write the function. So that's another thing to consider. Um, the ability to split the task into subtasks. As we mentioned, some computations are going to depend on the results of previous computations. So in those cases, parallel is not going to be extremely useful. Size of inputs, outputs. Again, um, if you need to pass a lot of data around, um, that means you're not going to benefit from parallelization, because you will incur a lot of costs with overhead. Independent sequential subtasks, it's similar to splitting the task into subtasks. Um, Local and remote computation. We didn't really touch on remote computation, but as I mentioned in the beginning, if you're using, let's say, Cloud Evaluate, you can pass it any parallel functions just as you would in a normal local kernel. And finally, there are some resources if you're interested um, in the topic and you would like to learn more. There's a list of a lot of resources, especially if you're interested in remote computing. You can read up on things like AWS and how you can use that from Mathematica, but it's a bit too niche to kind of include it in the main webinar. Another thing I want to mention before I kind of open it up to questions is that for some specific workflows, there are going to be there's going to be specialized functionality that does something in parallel that is going to outperform the built-in parallel functions. So the one I was thinking about, going back to the to getting informations out of web pages, obviously we can do something like parallelize, um, and we can pass it import, and we can give it some website. And if we have a lot of websites, that's going to make it quicker. But actually, for extracting information out of web pages, we have a special function called URL submit, which again takes a list of web pages and sends requests to them asynchronously. And the advantage of sending requests to web pages asynchronously is that you're not limited by the number of cores on your system. So URL submit is going to be actually faster for that specific purpose. So it's only going to work for getting information out of URLs or getting URL responses. But in that case, it's going to be quicker than the built-in parallel function. So if you are interested in some specific workflow, it's probably worth checking if there is something like that that is already available, because it might actually be quicker than trying to parallelize it. It's worth having a look in the documentation, and because there are a lot of built-in functions. Documentation is a good place to start. We also have Notebook Assistant, of course, which has access to all of the documentation. So if you are if you want to double check, you can always open up a Notebook Assistant window and ask something. It's been trained on all of the documentation. But other than that, yeah, just some resources here. This is just very basic for Wolfram Language. And I think that's it. So if you have any questions, I see there are some questions in the chat, which I'm going to answer now. But if you have any other ones, feel free to put them in the chat and I'll try to get through them.